Alright, welcome back. Today again an optional session, dimensionality reduction. Yeah. Why is this session optional? Well, mainly because it's a very technical session. And the golden rule is actually not to do dimensionality reduction unless you really need to. Yeah. There's two techniques we're going to take a look at. One is PCA, Principal Component Analysis. And the other one is SVD, which stands for Singular Value Decomposition. Yeah. Now, why do dimensionality reduction? Yeah. Well, we've seen in the lesson of K nearest neighbors that in higher dimension we face the curse of dimensionality. That means that the word distance, or Euclidean distance as we know it, does not make sense in higher dimensions. And in higher dimensions, all points are far from each other. So we have an issue. Yeah? When we talk about dimensions, we mainly talk about the features. Yeah? Remember, there's a feature vector x. This x1 could be the size of the house if you try to predict the price of the house. x2 could be the age of the house. x3 could be the number of rooms in the house, and so on. Typically we go to xd, and it means that there are d dimensions. Yeah? So there is a feature vector x that is actually d rows, one column. Theoretically it's d plus 1 rows and 1 column, because remember that we have set x0 to 1. Yeah? Okay, this I already mentioned. Only do it when needed. The second thing is that when we're going to do PCA, we're going to do mean normalization. That means that we're going to center the data around mean equal to 0. Yeah? If you want to get the intuition of what is actually happening with PCA, so here you have a typical data distribution. Yeah, this is a normal distribution, and in the normal distribution you can describe all your data by a mean mu and a standard deviation sigma. Well, the standard deviation gives you the variance or the spread of the data. What PCA basically does is it's going to center this curve around the mean 0, and while doing this, it's going to try to preserve the variance or the standard deviation. Yeah? So the standard deviation after the transformation of PCA should be as close as possible to the initial standard deviation for PCA. Okay, let's now take a look at PCA a little bit more in detail. What is PCA? Well, you're going to describe a large data set by a smallest set of relevant features. And the smaller set would be K, and K would be much smaller than D. Yeah? For example, in this situation, we could decide that the price of the house only going to depend on the size and the age of the house. So in this case, K would be 2 and would be much smaller than D, because there's many more features of the house that could influence the price. So we're going to transform a set of correlated data to a smaller set of uncorrelated data. Yeah? I give you a little bit of the intuition. Here you have a set of two features, x1, x2. Yeah? But you see that x1 and x2 are highly correlated. Means if x1 goes bigger, x2 will go bigger as well. So these features don't give you actually the maximum of information. Because if I give you x1, I already know that if it increases, x2 will increase as well. Yeah? So ideally your data is uncorrelated. Then it gives you the maximum information. So what are we going to do? We're going to reduce the dimension from two-dimensional, x1, x2, to one dimension. Yeah? And therefore we're going to find a vector. First of all, we're going to find this line. And on this line lays a vector a1. a1 is a unit vector. And we're going to project all these x's, which are the data points, onto that line. Yeah? So we project on that line. These are the little red stripes here. Yeah? And so we transformed our two-dimensional problem to a one-dimensional problem. We can call this Z1, for example. Yeah? But we want to keep the variance, meaning the spread between the data, as high as possible. Yeah? Just to give you a little bit of intuition on why this line is a good line, let us draw another line. Let us draw another line in blue, which is clearly not one of the better lines. Yeah? So this is the line in blue, and in green I'm going to do exactly what I did for the black line. I'm going to project the points to that axis. So in green you would have this. So okay, the green lines, yeah, they're definitely longer compared to the red lines. They're not only longer, but the variance has shrunk a lot. Yeah, this variance here is way smaller than this variance. Yeah, so this is not a good line. So we're looking for a line that minimizes the projection error and gives you maximum variance. And these two go together. Now some of you may be thinking, hey, but this is the same as we did with regression and finding the mean squared error. Well, it is not. Let us be very clear. This has nothing to do with regression and the mean squared error. And what's the difference? Well, first of all, here you go between features. Whereas in regression, you go between x and the label y. Yeah? So here's only features. Here is feature and label. That's one thing. And the second thing is we don't project these x's to the line. Yeah? We use vertical lines in this case. Yeah? And then we add them all up. Remember, mean squared error equals 1 over n, and the number of training samples, and is y predict minus the true y squared. Yeah? So it's something totally different from this here. Okay, now let's go a little bit more in PCA and derive some of the formulas.